Okay, so a graph relevant to a great many things. Is force measured in domino weights and length measured in centimeters. And we had a similar graph in the notes. You get a graph that's a relatively straight line. I commented more on the graph previously. It tends to be concave down, then concave up if you go far enough. Not sure you got into the concave up. I don't want to repeat that. You can reference that in the videos. Okay? So there's a slope to this graph, right? Okay, so let's say you got 1, 2, 3, 4, 5, 6, 7 dominoes here, right? So 7 would be about here, so we'll say 8's here, 4's here, 2, 1, 6, 3, 4, 5, right? And some length, whatever the length is. Let's just say that length, of course length goes on further, but let's say that here the length is 24 centimeters. Okay? So you get a slope. And you could divide this in half, so 12 would be about there, 18 would be about here. You can get the slope of this graph by estimating the coordinates of a point here and a point here. You can take any 2 points on the graph and you can sketch what I call a fundamental triangle. You get the rise and the run. Okay, so it looks like this point might be, that's 12, not 17, I was confusing myself. So that's maybe 16. My one's a little low. Let's just say that's 16.1. And this point is 36. Just a very approximate estimate, okay? Now that means 16 centimeters, 30 centimeters, right? And this means 1 domino, 6 dominoes. So that the rise is 5, and I'll put the units here, dominoes, right? And the run is 14 centimeters. That's not very accurate with the rubber band you got. The slope would be much greater, but it's okay. So the slope is 5 dominoes over 14 centimeters, which is about 3.6 or 7, 8 fourteenths. Dominoes per centimeter. Okay? So that would be your K for this particular graph, right? For this particular. Now, we say that if M is the mass of a bag in domino masses.
Wouldn't it be 0.36?
Yes. Watch me on that. Okay? Okay, so let's say you have a mass of 12 dominoes. Okay? Now we want to express K. Actually, I'm skipping ahead. We're going to express K in SI units. Okay? And that's something I wanted to talk about today anyhow. Okay? So this might be where you get a little confusion. I think I said, okay, I'm going to explain why I used the conversions I did. Okay? First place, SI units, kilograms, meters, and seconds, right? So SI kilograms, meters, and seconds. Okay? And I'm going to say that the mass of a typical domino is about 1/60th of a kilogram. So 60 dominoes is 1 kilogram. Now I've got domino weights and domino mass, right? Okay? Domino mass is different than domino weights. Weight is the force gravity exerts on the mass of the dominoes. Domino mass is just the mass of the dominoes. Kilogram is not a measure of weight, although it's often used that way even in some semi-scientific and even scientific publications, because people know the difference. Okay? It confuses physics students, which is a good reason never to do that, but who am I to judge? Okay? We're talking about people who communicate science much better than I do in some cases. Some cases people can't communicate at all, but they still use it, okay? You know, they're writing journals for high-level researchers, and they might not be good at communicating to introductory physics students. Anyhow, that's totally an aside, but I defer to the fact that I see this confusion all over the place, and in places where I wouldn't expect to see it, but I see it. So I live with it, okay? You have to distinguish between mass and weight, or force. Mass is not a unit of force. I mean, mass is not force, okay? Units of mass are not units of force. And that's really important to understand in terms of Newton's laws. Okay, so anyhow, 60 domino masses is 1 kilogram, okay? And then, 1 meter equals 100 centimeters. Okay? Now when I say 60 domino masses is 1 kilogram, it's not very precise, but it's actually probably close on the average. The dominoes have a lot of uncertainty, and we want to deal with that. Okay? Anyhow, we have this. If you do 60 dominoes, take 60 dominoes out of the box just randomly, they're going to be pretty close to a kilogram. Okay. So, what we get then is K is in dominoes per centimeter. Okay, we want to express dominoes in kilograms. So, what's the mass of a domino in kilograms? 60 dominoes, 60 domino masses is a kilogram, right? So, what's the, how many kilograms is a domino?
A 60th of a kilogram?
Yeah, 1/60th. I mean, you do the algebra, okay? You can divide both sides by 60 and you get 1 domino mass equals 1/60th of a kilogram. Do we understand that? It's very simple. So this is 1/60th of a kilogram. And what about centimeters? We want meters.
100.
I'm sorry?
Multiply by 100.
Well, no, if you multiply a centimeter by 100, you get 100 centimeters. We want 1 centimeter. This is 1 centimeter here. Okay, this is not a meter. If it was a meter and we wanted centimeters, then a meter is 100 centimeters, so we multiply by 100, right? Now, I don't know what you mean by multiply by 100, because ultimately that's what we do, but I'm not sure that's what you're saying. Thanks for the answer. Maybe it's right if you intended it the way it's going to work out. But if you intended just to replace the centimeter by 100 meters, you know a centimeter is not 100 meters, okay? You know, it probably takes you at least 5 or 6 seconds to run 100 meters, right? More like 12 to 14.
Yeah.
Okay? If you're really fast, 10. That's getting world record class. Okay. And you can run a centimeter a lot faster than that. Centimeter's only this far, right? So we want to think about those things. Okay, so centimeter is 100th of a meter. Okay? So we can say that's 0.36 times kilograms over meters times 1/60th over 1/100th, right? What's 1/60th over 1/100th?
100 over 60.
Yeah, because, you know, we divide fraction, we invert and multiply denominator, right? Okay? And everybody knows that 0.36 times 0.6 is 0.216.
It's 100 over 60, right?
You know what? And I'm actually,
How it is.
you know, this is kind of really wrong. I'm going to do it anyhow, then I'm going to fix it. Okay? I'm doing this in domino mass, okay? And that's not the right conversion for domino mass. But anyhow, we get 0.216 kilograms per meter. Now let's fix it because it's pretty easy to fix. Okay?
Isn't it also 100 over 60? Not 60 over 100?
Yeah. Okay? So I wrote that down carelessly. Okay. Let's fix a couple of things. First of all, that's wrong. Second of all, that's wrong. It's going to be 0.6. Now, officially I'd write 0.60, so I'm going to write it. That second significant figure, it might actually be significant, it might not, but it's close enough that we'll write it. Okay? So that's, yeah, times 100 over 60. Okay? Now, the thing I did wrong here is, yeah, that's domino mass, but this is domino weight. Okay? So I should have been more specific when I wrote this, because I just looked at that. And, but the mass is 12 domino masses. So the conversion to correct it is actually pretty simple. First of all, the unit of weight in SI is the Newton. Okay? And we'll see why that is shortly. You know, we've talked about Newton's second law a little bit, but we haven't talked about the units. So this is going to be in newtons. So this will be in newtons, and this will then be in newtons per meter and newtons per meter. I didn't realize until I got down here, I got kilograms per meter, that I'd been following an erroneous okay? So it didn't make sense when I got down here. Now the other thing is, my conversion factor isn't quite right. Okay? We take the 0 off of that 60, and you'll understand why. But right now, we're just trying to get a handle on that quite important phenomenon. So my 60s should all be 6s. Which means this should be 6. Okay? Now the process is identical to the other, but this is the process that we want to use And this is not domino mass here, this is domino weight. So it's rather easy to fix that. Everything I said about how you convert the units is right. I just had the conversion for domino mass, where I should have had the conversion for domino weight. Okay? You make that change, everything is really pretty simple. We get this. Okay? Now, back to domino mass, the conversion is what I said. So, $60 domino masses is 1 kilogram. If we use that, we see that this is 12 times 1/60th of a kilogram, or 1/5 of a kilogram. Okay? So that our payoff, and I hope you reviewed the notes from last time, but it comes down to, for this oscillation with 12 dominoes, with this rubber band, that omega equals the square root of k over m, which is the square root of 6 newtons per meter divided by 1/5 of a kilogram. That's the square root of 30. And as you're going to see, probably shortly today or at least next time, okay? When you divide the newton per meter by the kilogram, you get reciprocal squared seconds, seconds to the -2 power. And the square root of 30 is about 5.5. And that's in cycles per second. It's not in cycles per second. You know, got no excuse. I slept pretty well, feel pretty good. Just being a little careless. Sorry, it's radians. Per second. Okay? Now, how many radians are there in a complete cycle?
6 point something.
Well, 2 pi. What's pi?
3.14.
Yeah, you don't need more than that. It's about 3, because these are all very approximate conversions and everything. So you get about 3. Okay? So 2 pi is about 6. So this is pretty close to 1 cycle per second, right? Now what that means is the rubber bands in that bag ought to be oscillating 1001, 1002, 1003, 1004, about that fast. Okay? Now these are not realistic numbers. You have your data. You find out what your numbers are and compare that with the oscillations of the dominoes. Okay? Now John, you weren't here in lab. And hopefully we've got good data reports that I can share with you.
Did you hand out a bag of toys for class?
No, I was going to give you some,
Or is it just
since you missed Monday.
Yeah.
So we're going to figure out what to do about that.
The data wasn't on the website.
I'm sorry?
The data wasn't on the website. So if you did,
No, you have the data.
well, yeah, but
You took the data. It's your data. Everybody took data on all these things. Okay?
Mhm.
So, if there was a little confusion about what I asked, does this clarify it? I mean, that's the whole process right there. That's what you do. And of course now, we can see how that relates to what we did last time. And if you understand the calculus, you understand where omega came from. Okay? Haven't seen, I'm not seeing many of the problems that I assigned, so we'll have to figure out how to get that done. I can't actually do it for Wednesday because it's a pretty long assignment. We'll figure out how to parcel that assignment out to a couple other assignments. Okay? I want something on Wednesday. But I'll figure that out later. And then we'll have lab on Friday. And we'll pretty much go every other Friday unless there's a conflict, but I think I might have put in the website at some point, or on Compass. And you were right. For some reason, the physics site wasn't active. All the others were, and I think I just didn't click in the right place or something, and then didn't double check it. My fault. But I was dealing with the fact that I had no access to any of my stuff at the time I did that. Not an excuse, but
it's pretty
slack on that. Okay. Okay. So you should find that when you do this graph and use these conversions, and you don't have to. And I think I gave you the conversions correctly on the paper, okay? Because I know I was thinking straight when I did that. And I didn't have something on the board that caught my eye and distracted my feeble brain, okay? But now, this is the reason behind the conversions, and I expect you to understand that. Okay, you don't have to use it in your write-up, especially if you've already given me a write-up, okay? But I expect you to understand how to just take how many of these equals how many of these and be able to convert these to these and these to these, right? Very simple. Your textbook will have a more complicated version of it, which is also good for bookkeeping. But this is the quick and dirty way that I actually prefer. It's the way I think. Okay, but you should be able to reconcile the two. It's simple enough. There's nothing more than a little bit of algebra with fractions involved. Okay? But you got to treat the units as algebraic quantities. Okay? Okay. So again, your slope here and your angular frequencies here and the frequency of oscillation should reconcile very closely, which ought to convince you that the linear model for the rubber band is reasonably accurate. Okay? Now, why is this important? Then I did want to review this a little bit. Okay, well, what's our basic premise for simple harmonic motion? And this is really what I want you to see. The net force is negative kx. Okay? Now I'll point out that F net equals negative kx would imply a graph of net force versus position that goes through the origin, because when x equals 0, F net is 0. Okay? This graph doesn't go through the origin, does it?
No.
But this point here is the equilibrium point. Okay? So if you measure displacement from equilibrium, you're going to measure displacement from this point if you're doing a graph of F net equals negative kx. Okay? So what we have for the domino bag is the F net for the rubber band would be measured from this axis, and you would have a straight line through the origin. So that means, I'm just drawing a little schematic, that's what the graph of F net versus X looks like. It's got a slope of equal to K. Just a straight, simple straight line, simple proportionality, a direct proportionality. So we have this. Make sense? And this implies that X double prime equals negative K over mx, which implies that X of t equals a cosine of omega t plus phi. Now that's a synopsis of what we developed last time over a period of 45 minutes or something. Okay? But this basic outline is something I need you to know. Always, the idea of premise leads through just plugging into details and doing a little mathematics to the conclusion. Okay? There's a little calculus involved in this. You just have to know derivatives of sine and cosine and a little chain rule. John, have you had calculus?
Yeah.
Okay.
Calculus too, I believe. Miss Fleming, is she still here?
No, she retired. She did real well.
Good, she was fine.
So it's been a little while. And it was,
Yeah, I pretty much haven't had math in about 5 years.
yeah,
so
well,
I'm
we're going to need to review the calculus, but it's
jumping straight into it.
yeah. So, you know, I need to know that. So I tell you what to review. I've told everybody, but I don't expect you to go through all the videos to dig out what I've been telling people.
Yeah.
So you need to, at this point, you need to just know the basic derivatives of power functions and trig functions. Exponential functions too, and the chain rule. And I noticed that even people that had calculus last year are fuzzy on it. So if you're fuzzy on it, maybe you're a little fuzzier than they are.
I've got 2 or 3 notebooks full of stuff to look through, so.
Well, you don't need to look through that much. You just need to get down the rules for those things, and we'll be talking repeatedly about what it all means, because nobody comes out of calculus know what anything means. It's not really true, but that's all pretty fuzzy. Okay? So that's what we've got, and that is nice full circle with what we did last time, which I wanted to review a little today. Okay? And I also wanted to talk about notes. So your first question, the first thing you didn't understand, leads to quite a bit of good information, I think. Okay? Got it?